Okay, so PowerPoint 4, we're going to talk about precision, accuracy, and error. So this conversation is going to reside in the determine appropriate data phase of our problem-solving cycle. So we're still talking about the data, we're still talking about how we interact with that data. So the concept of error basically is that no measurement is perfectly accurate or precise. There's always going to be some amount of uncertainty in our measurements. We can term this uncertainty error. So this term error is what we're going to use as basically not 100% accurate or precise. And those two things are different. We may use them interchangeably, but we're going to go through in this presentation and distinguish between the differences between those two terms. So looking at systemic error, basically these are errors that are the same size and basically have the same algebraic sign. Basically they're all positive or negative in relation to what we should be measuring if we were perfectly accurate. And so systemic errors, measurements that are repeated several times, the same size and the same algebraic sign. Random, on the other hand, caused by all different kinds of things or reasons, and they have lots of different values. So we can make 100 measurements and our variation could be all over the place, right, randomly, okay? And it's based on conditions like environmental conditions, heat, temperature, humidity, those types of things relate to random errors. If we look at an example, systemic errors being things like incorrect calibration or using the wrong units, or even just as simple as we didn't set up the fixture properly or we didn't measure it correctly per how we were supposed to measure with that piece of equipment. Random errors being factors like operator error, environmental fluctuations, humidity, temperature, like I said, things that happen that aren't consistent. Okay, those are random errors. And random and systemic errors are commonly both happening when we're taking measurements. So there's a little bit of both at a lot of times when we take measurements. And when we talk about accuracy, systemic errors determine the accuracy of a measurement. Okay, so we can relate systemic with accuracy. We can again relate random with precision. So random errors determining precision of a measurement. Now it's very important to note that precision does not necessarily imply accuracy. Okay, those are two different things like we said. And a precise measurement may be inaccurate. Okay, so we may have a very precise measurement, but it's not very accurate. And we'll see what that means here in a second. So when we talk about accuracy and we talk about precision, we can put them in this like 4-quadrant diagram with accuracy on the left and precision on the top, and we have high and low for each. And if we talk about accuracy, accuracy is basically how close to the target are we. So if we have low accuracy, all of our values that we measure are pretty far away from the actual bullseye or target. No matter if they're spread out or if they're clumped, they're still far away from the center. So that's low accuracy. Now if we look at high accuracy, they're much closer to the center of the target. Okay, they may not be tightly grouped, but they're still much closer to the center. Turning to precision, now that's how tightly grouped they are, right? So again, when we talk about precision, we don't care about how close they are to the center of the target. We just care how close they are to each other. Okay, so high precision, closely grouped. Low precision, really far grouping. Okay, and so we can have something here that is on the left, further apart in grouping, on the right, much tighter in grouping. And then, of course, between that, we can throw in accuracy, and we can combine these two terms, right? And we can see that high accuracy, low precision, right? It's tighter grouping, closer to the center, right? Really, ideally, we want high accuracy, high precision, right? But we should always remember that both precision and accuracy are a lot of times at work. And the causes of those are the systemic error for accuracy and the random errors for precision. So again, just restating some things I would just commented on. Measurement has high accuracy if it produces the correct value on average. So if we would take an average of all our measurements, and on average it was the target value, that would be high accuracy, okay? Because on average we get to that target bullseye. Systemic errors can be minimized by calibration, okay? So if you have an inaccurate measurement system, first thing you should do is calibrate it. You do this when you step on a scale in your bathroom. Precision, on the other hand, right? Measurement has high precision if it shows little variation when the same object is measured repeatedly. So there's small random error. So you repeat that measurement and you don't change too much between 1 inch and 1.5 inches, right? Very, very precise measurement. Or 1 1/4 and 1 1/8. Random errors, of course, are statistically quantifiable. So we can actually use statistics to describe and predict how much error, random error, we're going to have in a measurement. And that's a very big part of statistics that is very commonly used when we take measurements of processes and measurements of physical things. So random error can be reduced by repeated measurements, okay? So how do we get rid of random errors? We just take 100 measurements and we get an average of all 100, okay? How do we get rid of systemic errors? We calibrate. So this is how accuracy and precision are different, and this is how precision is related to random error and accuracy is related to systemic error, okay? So now let's pull error apart a little bit and let's kind of build an equation to help us calculate error. So if we look at absolute error, starting at just the difference between the true value and the assumed or the approximate value n bar, which is what we measure. So if we say that n is the gold standard, okay, n bar is what we measure. We basically say what we measure minus what it gold standard, that's how far off we are, right? And I think we can all understand that and agree to that. If we want to look at a relative error, now this gets a little more permutations of this equation, but a relative error basically saying what's our error in comparison to what it should have been. So what's the ratio? Okay, we would just say the error based on what we calculated in the previous slide, n bar minus n divided by n. So this will give us a ratio, okay? And of course we can pull this apart and we can have the two parts n bar divided by n minus n over n. Of course n over n just simplifies to -1. So that's where we're left with relative error is just n bar divided by n minus 1. So this is how we've built this equation. And we haven't changed anything through this equation. We've just kind of simplified it down here. So that's a relative error, a ratio. We can then look at percent error. So how far off percentage-wise are we from what our gold standard is? So we measured something. How far of a percentage off are we? Okay, of course, we can just take our relative error and multiply it by 100 to make a percentage. And a way we're going to do this is we're going to write this out like we did previous, n bar minus n, or n bar divided by n minus 1 times 100. That number will be a percentage. So if we get a value equal to 0.5, that is 0.5%. It is not 50%. So the answers we get from this equation are already in a percentage form based on multiplying by 100. So of course, it's important now the sign or the negative or positive of that result. Negative meaning that we're below our target measurement, positive meaning we're above. We could write a line here, and this is our target, and if we're above here, we're in a positive, if we're below, we're in a negative. And then of course we get all these measurements, some positive, some negative, that go, the different measurements we make. And of course, this is our variation, right, from our center line of our target, right? That's our error. and the percentage off we are. If it's a positive, it means we're above, negative, or below. Some different ways of getting error in the different analysis we can do. We can do truncation error, which is basically a rounding error from rounding off numbers. So if we say we pull a number from a conversion chart, and instead of using the full number, to this many decimal places, we just round off to 2 decimal places, we would have a negative 0.05%-ish error, right? So what we measured on top, what it actually should have been, okay, minus 1 times 100. So we're actually, this number, 3.14 for pi, is actually 0.05% below, that percentage below what it should be in reality. So that's our error, it's our negative error. Another truncation error, say we use algebra to represent a function instead of a pure calculus function. So algebra being chunks, right? Little segments, like digital segments. Calculus being continuous, analog. Of course, anytime we just take a slice of something, we're going to input error into that result. So that's what we're doing when we say this truncation error here. If we use just one term, pi divided by 2, that is 57% off what the previous function here would be. If we use 2 terms, okay, now we've gone much less percent error, but we're still negative 0.75 off of our actual if we would use the full calculus equation. Okay, so there's just another example of how we get error in the way we calculate. Okay, algebra is a lot easier, but it, as you can see, it's inherently has some error to it. Interpolation error. So let's say we have a situation where we want to approximate a value. We have a diameter 10 millimeters. We have another diameter 10.6 meters and a third diameter 11 meters. And we know the circumference of 2 of them, but we want to approximate the third. If we look at this, this middle circle is 6% larger in diameter than the first one. Okay, so we could approximate that and say, well, then the circumference is going to be 6% larger, right? So we'd calculate circumference of the 10 meter circle times 1.06%. We get 33.3, 33.1, depending how we round. In reality, that is negative 0.03% off. Now, a negative 0.03% is very small, right? Possibly, but we still want to see that we have that error, okay, because we approximated a value. Again, we can approximate by using a decimal value versus a fractional value of a number, and we can get percentage off. Really, the takeaway here, this is a positive error, so we know that the value we measured was greater than the value that we should have had, okay? Whereas a value that's negative, a result that's negative, meaning we had a smaller value to start with. Of course, as technology students and technologists, we oftentimes bridge the gap between theoretical designs and the real-world application. So we're a lot of times taking something on paper and putting into practice in the real life, the real world. And a lot of times, that's when errors come into play. So we really have to be careful. We have to remember how to analyze error and also that it's a real thing. And so just to wrapping up, we need to know how to calculate and quantify our errors, and we're going to use that error equation throughout the semester. And we want to understand the sign, okay, so we want to understand that the sign means something. It'd be helpful to also understand how to manipulate the error equation, how to rearrange it. And the proper significant figures and rounding have a very significant effect on error. Okay, that's the number one thing that we'll probably deal with. It will input error into our equations.